Hey folks, this is that video I promised recently. I wanted to go over the quiz, finished grading them, and I saw some common themes and common confusion I thought I would address. So there is a link for the solution key. It's a Google Doc, and that's in one of the Blackboard announcements. But this will be a bit more conversational. So the first one, people overwhelmingly get right, and the idea, excuse me, is if you want to know if these are linearly independent, then what you're always doing is taking a linear combination of these and asking this question, which always leads to a matrix equation. And right, the question is always, obviously A, B, C, and D can be zero. That's one solution, but is it the only solution? If it's the only solution, then they're linearly independent. If it's not the only solution, then they're not. And, really, if I were being a bit more careful here, this should be a column of zeros. So that all depends on the determinant of this matrix. And the determinant of this matrix is, in fact, 0, right? Which means the vectors are linearly dependent, which means they're not a basis. And just automatically, because it can't be a basis if they're not linearly independent. So done, check. But folks got this first one correct. The next one says, which of the following is or is not a linear transformation? And there was varying degrees of success here. And so let me just kind of walk through how you should approach this. To determine if something is a linear transformation, you have to check two properties. And for the most part, that's the best way to do it, to directly check that this holds. There are some other ways of doing it, and some people did those ways well, and some people did not. So that's the definition. If a transformation T does these two things, it's linear. So for number 2, we're given this D1, which maps capital F to capital F, and the action of D1 on a function f is f prime plus f. So if we want to know if this is a linear transformation or not, then we have to check. So I would take D1 on a scalar times f. So that would give me AF prime plus AF. I mean, AF is a function, so if you think of this transformation, it takes whatever you give it and gives it a derivative plus the thing again. This is a derivative plus the thing again. And if you work this out, this is AF prime plus AF. This is A times F prime plus F. And that's A times D1 of F. Whoops. And so I've started over here, and I've ended up over here. I've demonstrated that the transformation preserves scalar multiplication. Now, I can take two functions, f and g. Again, this is the transformation that gives me a derivative plus the thing. So I put the sum in both of these. And then I use what I know about derivatives. The derivative of a sum is the sum of derivatives. Then I can regroup these, f prime plus f plus g prime plus g. And this is d1 on f plus d1 on g. So I started over here and I ended. So this is why it's a linear transformation. Now, a couple of you, only a couple of you, argued successfully that d1 is the derivative plus 1, and that the derivative is a linear transformation, multiplication by 1 is a linear transformation, And we're told in a theorem that if you add linear transformations with the same domain, it is again a linear transformation. And that is a completely legitimate argument. So that's fine too. Let's try the next one. So the next one's a little different. So we're told that it's D2 on F. This is a transformation, and it's F prime, I think, plus F. Yeah, sorry, plus 1. So I'm not going to make any arguments right now about whether or not this is or is not a linear transformation. Instead, I'm going to check. I'm going to start with a scalar multiple of F. What does this thing do? It gives me a derivative plus 1. All right, so that's AF. The derivative of AF is AF prime plus 1. And now notice I cannot factor I cannot factor an A out of here, right? I want to get to D2 on F, and I can't. This wouldn't work. So I can stop right here. If it fails one property, it doesn't matter if it fails a second. It's not a linear transformation. This is how you check that something is or is not a linear transformation. Start with something, and then carry it through and see where you end up. All right, that was number 2. Number 3, let L be a linear transformation from F into F, where L of F is F prime minus F. And then we're going to find some results. So 3, we have this L of F. The effect is F prime minus F. And then for A, we're looking for which F's go to 0. We're basically looking for what's in the kernel. So how do I deal with this? Well, this question is really about practicing notation. So L on F is F prime minus F equals 0. That's F prime equals F. And so F of T is going to be a multiple of E to the T. Make sure you get all of them in there. That's every multiple of E to the T. Now for B, the equation is a little different. It's L of F equals 1. Well, L of F is still F prime minus F equals 1. So this is another first order equation. And you can solve this with separation of variables. This is df over 1 plus f equals dt. This is ln absolute value of 1 plus f equals t plus a constant. This is, let's see, 1 plus f equals some constant e to the t. And then f of t would be equal to a e to the t minus 1. So this is practicing with notation, because if you understand what this L of f is, it's just this stuff, then it immediately turns into a differential equation from chapter 1. Exponential, or, so this is a homogeneous equation, this is non-homogeneous. That's what 3 is. All right. Number 4. So this was commutation. And for this too, you should be showing things. So d plus 1, d minus 3, or rather, comma. Do these commute? Well, they commute if, question mark, if you get the same thing, whoops, multiplying them in both orders. And we will here because everything is constant, because d of minus 3 will be minus 3d. So I'm going to write it like this for the moment. And then over here, I have d plus d1 minus 3d minus 3. And the important bit here is that this is the same as minus 3d. This is the same as 1d. And so they are the same. Now, in contrast, the next question, they're not. And the next question, I would say, is even more important to show me why they don't commute. Don't just say, no, they don't, but do it out. This is d squared plus d minus td minus t versus d squared. Now we have d minus t plus 1d minus t. And this is the important stuff here. These are not the same. These are not equal. So you're showing that it's not equal. Okay. A lot of folks get these fine. 6, there was some confusion. So for 6, I'm asking you to identify some notation. So let's just jump right in. So if I have t squared x triple prime plus 2tx double prime minus x equals sine of t, and I'm looking for you to identify what L and F are. This will be important because a lot of the methods of chapter 4 are going to talk about L and F and what to do in different scenarios. So really the idea is I would first write this out as t squared d cubed plus 2t d squared minus 1 on x equals sine of t. And then just make some note. You could highlight, in a Google Doc, you could highlight this with a certain color, or you could say L equals this or whatever. This is L and this is F. And it's okay for L to have non-constant coefficients. That is certainly all right. So that would be A. Let me see. And then B is x double prime minus x prime plus 3x minus 4t plus 1 equals 0. Now we have to move some stuff around. This stuff is going to have to go to the other side. So I'm going to have 2 derivatives minus 2 times 1 derivative plus 3 on x equals 4t minus 1. That's my L. That's my F. So these equations, even though they're quite different, still have this basic form of a linear transformation acting on a function, giving you something else. And then let's see if I can fit C in here. So C x triple prime equals 2x. So again, a little bit of moving stuff around. So x triple prime minus 2x equals 0. That's d cubed minus 2x equals 0. D cubed minus 2 is L, and that is f of t. F of t can be 0. That's a homogeneous equation. So that's all I was looking for there, was the ability to identify what part of the equation was the operator, what part is the function, what part is the non-homogeneous part. All right. What's next? 7. Right, this was finding a basis for d squared, for the kernel of d squared. So this confused a lot of people. So if I want the kernel of d squared, let's think about this a couple different ways. One, I can just go ahead and solve this differential equation, which is x double prime equals 0, which is x equals a t plus b. A lot of you mean, fortunately, we're going back to Top Hat to look for information, and you kept homing in on one particular solution. I think I had a question which said, what was in the kernel, whatever, 3t minus 4 or 3t minus 2, whatever it was, is in the kernel. But there are lots of things in this kernel. There's an infinite number of solutions to this equation. It's a general solution. In terms of a kernel, one thing we can think about is that what sorts of basic functions are in here? We want a basis for this kernel. Well, constants and multiples of t. I mean, you think about this general solution, and it's a times t plus b times 1. So one possible basis is just t and 1, right? This would be a basis for the whole kernel because everything in the kernel can be written as a linear combination of these two. It's not the only one. Some people wrote some different stuff, and I don't know where they got them, but if you wrote something like this and this is also a basis if it's linearly independent, which you can find out. I mean, if it's not a very obvious basis like 1 and tr, but you could certainly work this out and get 3a plus bt, and then you get plus minus 2a plus b equals 0, and you could set this equal to 0, set that equal to 0, and so you've got 3a plus b equals 0. This is, again, not what I'd recommend doing, but it certainly can be done if that's what you'd want to do. But it has a non-zero determinant, so blah blah blah. But this was what I was going for. It's all linear functions, and so the two things you need to write a linear function is t and a constant. And any constant will do, but one's the simplest. All right. And then lastly, 8. So A was just basically asking you to recognize that the kernel of L is always a subspace. That's why. Although it is worth noting that the reason it's always a subspace is that if you were to, you can take two solutions, and if you add them together, then you're still going to get 0 plus 0. So adding solutions works. If you add a scalar multiple, that's going to work. Yeah, there's always inverses because you can just factor out the minus sign, and so on and so forth. 0 definitely always works. So the kernel is a subspace because of the properties it has. I'm going to skip B. Everyone got B right. C, though, so this was bonus because I thought it may be a little harder. The equation is Lx equals 1, and do the solutions of this form subspace. And you won't know, generally speaking, until you try. So don't say yes or no offhand. Try something. For example, is 0 in there? No, because L of 0 equals 0, which does not equal 1. So there's no 0 in the collection of solutions to this equation. So that can't be a subspace. It doesn't have 0. It also doesn't have sums. If you take two solutions, x1 and x2, what are you going to get? L of x1 plus L of x2. These each give you 1. So this is 1 plus 1. That's not equal to 1. So you can't add solutions together. You can't multiply solutions by a number because you could factor that out. And then you'll get a times 1 equals a, which doesn't equal 1 unless it's a. It doesn't have inverses, for the same reason. So this really fails in almost every conceivable way. So the kernel is quite special. Lx equals 1 doesn't work, Lx equals 2 doesn't work, Lx equals any number, any non-homogeneous equation doesn't. So the kernel is a very special subspace. Okay, that's all I've got for this. Hope this helps along with the solution link. Thank you.